$5. The first person on is Harold Locke.
It looks like you're drinking out of a nebula. That your bottle disappears into the background, just like
The Milky Way is my nourishment.
Milky Way. What flavor is that Milky Way?
Watery.
You feeling better?
Yeah, I'm feeling a lot better, actually.
That's good. Yeah, you sound it.
Got a little bit of a cough still, but a little tons better compared to Monday. So yeah, if you want to go over a list on what you want to try to image tonight, if it clears up.
Yeah, I'll have a once we're done with this, I'll go and make a cup of coffee. I'll have a quick look at Stellarium.
Yeah, and then we can set up something, because it won't take long to set up this guide scope, because I've already got existing rings. We just we'll focus it on the NCP, because that'll be the quickest. And yeah, I can just set it up sharp cap to get it there. And then we can go off and get it done. Then the other guide scope will be here Monday. They got pushed. Monday or Tuesday, depending. So I get the rest of the stuff off to you later.
Yep. You want to buy a jetpack? There's a company here in Christchurch called Martin who make personal jetpacks, or they've been trying to produce them, but they've gone bankrupt, and they're selling off all the prototypes.
Is it water or hydropulsion, or
No, it's a proper
jet fuel
flying aeronautical jetpack.
Oh, nice. No, I'm good.
Fly to work on your jetpack.
Well, singeing the back of your leg hairs, or just taking off your legs.
Are you going to get one, Simon?
So again?
Are you going to get a jetpack?
Yeah, I can just imagine landing on the roof of our car park on the opposite.
How much are those jetpacks? How much do they have listed?
Oh, well, the one they've got at the moment is about $1,500 US.
Oh, that's
I don't know how
Come on,
No, I don't know how serviceable it is.
My next question is, how big is this jetpack? That sounds tiny.
They're pretty big. Yeah.
People spend that on an astrocam, right? A jetpack.
Yeah.
Oh yeah.
Sure.
I've got a car park space. It's on the roof.
I'd like to get or the wife's trying to talk you into it. So
that's going to have to be a hard pass for me.
Yeah.
I'm afraid.
Depends on how fast the wife wants to get rid of you. So
yeah.
No hard, you need the jetpack. Yeah.
She can think of quicker ways, I'm sure.
I think you can probably think of quicker ways as well.
I could.
Just go buy another camera. We'll see how long you last.
Why you got to go there for? Why you got to go there? I thought we were friends.
Yeah. It's called reality.
It's called reality.
Yep.
The ugly truth. right?
The ugly truth. It is 4 o'clock. Let's get this countdown trucking.
It's,
4. No, that's 11.
You guys ready to go?
Let's do it to it.
Let's do it. Okay.
It took a dark, unassuming patch of sky to find galaxies twinkling at the edge of the cosmos.
For the Hubble Deep Field, it was important that we get a essentially unblocked view of the distant universe. We want it to be unblocked by anything in our own galaxy, that is bright stars or dust in our galaxy. We wanted to avoid any bright nearby galaxies that might have essentially dominated the picture. And so we had to do some studies to find a field of sky that was essentially boring in every way, so that we could look at the distant galaxies.
The team targeted Hubble's continuous viewing zone, narrow patches of sky near the North and South poles, where Hubble can stare for several days without being blocked by the Earth. The long exposure brings out wispy detail in galaxies as far as 12 billion light years away, but the telescope also captures light that astronomers need to filter out.
The problem is that the telescope itself is subject to radiation from charged particles, most of which come from the solar wind. And those also leave little spots of light on the detector. And so when you see one of the Hubble images, it's covered with these spots, like measles. So you have to take a whole bunch of pictures. These spots will move around because they're not on the sky, but the galaxies and the stars will stay there. So you take a whole bunch and you combine them together, keeping only the things that don't change from image to image.
In all, it took 350 images with 3 different color filters for the team to piece together the final Hubble Deep Field image.
Well, the thing that amazes me when I look at the Hubble Deep Field, first of all, is just how many galaxies there are. This tiny spot on the sky, and almost everything you see in the image is a galaxy. Each of those galaxies has anywhere from 1 billion to 100 billion stars in it. So we have before us in this image the history of the universe, if we can figure out what it's trying to tell us. And in many ways, it's like going out on a very dark night and staring up at the sky, and you realize how tiny a part of the sky it is, and yet you're seeing these vast systems of stars. What an amazing universe it is we're looking at.
Muted.
You're on mute, Scott.
You're on mute, Scott.
Muted, sorry. Hi, everyone. If you were reading my lips, this is Scott Roberts from Explore Scientific and the Explore Alliance, and this is the 19th Focus on Astrophotography program. And today, Tyler Bowman has a special guest, Simon Lewis from the Canterbury Astronomical Society in New Zealand. So I'm going to turn this over to Tyler.
Oh no.
Here we go.
Oh no. How's it going? Oh no. Now I'm nervous.
You're nervous now,
Now
huh?
I'm nervous. Hi everybody. Tyler here with obviously with Explore Scientific behind me. We have a man from the future, believe it or not, that's with us. Our very own Simon Lewis. Simon, how long have I known you? We've been, I hate to say the word friends now, for what, a little over a year?
Yeah, something like that. Yeah.
And Simon's, excuse me, Simon's a very well-known, and again, I'm going by my opinion, a well-renowned imager in New Zealand. He helps run the Canterbury Astronomical Society in New Zealand, which I plan on going to New Zealand with my wife and myself, hopefully soon. I'm leaving the kids here. Scott can watch them for all I care.
Yeah, I'll watch him.
I want the clear skies. I really do. God, what's your bortle? A 2?
Yeah, I'm in about a 2-3 here, just depending on what the humidity's like. But yeah, generally 2-3.
But the premise of the show today is we're going to talk about pixel scale, and Simon's going to be here. We're going to talk about the effects of oversampling, undersampling, and reducers as well, because we need to talk about reducers because that can help with some oversampling that you're having. But again, I'm going to turn it over to Simon now because he's going to be the lead presenter. Simon, floor is yours.
Yeah. Well, okay. So Tyler wanted me to talk about pixel scales, and one of the key questions I get asked on a regular basis is which camera should I buy? And that really is like how long is a piece of string, because there is quite a number of things that you need to think about when buying cameras. If you look at a camera on a website, you will see a whole bunch of specifications for that camera. There's different sensor sizes. The market is covered with cameras from small 11 millimeter sensors, or planetary cameras even, which are even smaller, all the way up to sort of full frame and even beyond full frame, depending how deep your pockets are. But there's one thing that is really critical about all of these cameras, apart from things like the efficiency of them and whether they're a monochrome sensor or a color sensor, but that is the pixel size that the camera has. And this is the actual usually measured in micrometers, because the pixels on them are usually quite small. And the size of those pixels really is important when you actually start to look at your overall system and start to engineer what you want out of your system. So we measure these in micrometers because usually they're the pixel sizes on these cameras are really, really tiny. You're packing thousands, megapixels of, millions of pixels into a few inches of silicon wafer on the back of these cameras. And the groups of these pixels can be, anywhere between 2 or 9 micrometers. So that's how small these little groups are, and they're usually grouped together either as a single monochrome pixel, or in the case of a color camera, they'll be grouped together in what's called red, green, and blue, and that's what gives us the color. Now, we talk about pixel scales, and that's how well our camera captures the light and turns that into an image. If we are either way on the scale, we can be capturing the light over too many pixels, or we can be capturing the light over not enough pixels, and that will give us a couple of different scenarios. And this is called undersampling or oversampling. But a pixel scale is we usually measure these in arc seconds. And if you're not really familiar with what an arc second is, if you hold your thumb out in front of the moon, you can usually block the moon with your thumb. That is about 1 degree. And if you then take that in a much smaller scale, if you start breaking that 1 degree into a smaller group, you can come into what's called an arc minute, which is 1/60th of a degree. And if you go again, arc minutes down into arc seconds, and that's by another 60. So we're talking about 1/360 of a degree, which is, if you think about it, 1 arc second is about looking at a coin about a couple of miles away. That's how small an angular distance that is. The reason that we're interested in arc seconds is that our atmosphere limits the resolution that we can achieve in our images. For most locations on our planet, unless you live on the top of the Atacama Desert, most objects that we see will be blurred over about 2 arc seconds. Now, light coming in from stars, for example, if you're outside the atmosphere, they could be much tinier, even sub-arc second. But by the time they get through our atmosphere, because of the blurring effect of our atmosphere, they're usually about 2 arc seconds. So how do we calculate what our arc seconds per pixel is? That's the first step. Well, you can use maths. There is a little bit of a calculator, which is basically the pixel size in micrometers divided by the focal length of the telescope, and that'll give you what the angular resolution is in arc seconds per pixel. And in general, the longer the focal length of the telescope, then the smaller the arc seconds per pixel that you're seeing. So if you're using a small 80 millimeter, then your arc seconds per pixel will generally be much larger than, say, using a large Schmidt-Cassegrain, which will have be able to see a very, very small portion of the sky. So the way that you can calculate this is, if you're not very, very good at maths, there's a couple of really nice websites that we can look at here. But in general, why do we care about whether we have a certain pixel scale? Well, if you have a large pixel scale, and pixel scale is usually the key. The golden point is basically 1 arc second per pixel. That's usually the best. Although we've already said that our seeing is usually not better than 2 arc seconds per pixel. Then what can happen is that the light can actually either spread across more pixels than we really, really wanted, and you end up with very sort of bloated stars, or what we call oversampled. You lose sharpness in our images. Consequently, the other way, if we are undersampled, if the light from the star is only illuminating a very small set of pixels, you'll end up with blocky stars. And you can see this effect if you zoom into an image. Then what will happen is that you'll zoom in so far and you'll see that sort of pixelated view of what it looks like. It starts looking like a very pixelated view of the image. So I can show you this effect here if I share. If I just share this, I think. So, okay. So you see my screen here?
Yes.
So our pixel scales here. So if we are, we were talking there about undersampled stars, and this is really, really where, if you can imagine, these are the pixels in the camera, and the light from them is only illuminating a very small number of pixels. So you end up with this sort of very sort of blocky looking. I mean, these are generally cosmetic desires. I mean, you're still seeing the light from the star. You're still detecting it. But if you want to have, cropped images, for example, if you want to crop in a certain area on a nebula or a galaxy, then having good sampled data is easier to work with. And consequently as well, if you oversample, if you have the light from the star over too many pixels, now you'd think that wasn't potentially a bad idea, but actually what happens is you get this blurring effect through the atmosphere. So it actually samples over too many pixels. You end up with these sort of very wide, very bloated stars. And both of these are something that astrophotographers don't really aim for. Neither of them are terrible in terms of, the final image.
Simon, we just lost your audio.
Uh-oh. Scott, do you want to recognize some of the people in the audience?
Yeah.
There's quite a bit.
Time. Yeah, since we got this quiet time right now. That's right. So we were trying to decide who was going to be the first one to log in today. Yep. It ended up being Tarek, okay, in UAE. Yep. Second was Richard Grace. Pekka third. So Pekka says, howdy, everyone all over the globe. Martin Eastburn is on. Says howdy from East Texas, and howdy Scott Roberts, Scott, Richard, Tyler, and Tarek and Pekka. Matthew McAlilly, hey y'all. That's right. Let's get a hey y'all from Mississippi. Clear skies here, and I'm headed to the Rainwater Observatory.
Nice.
We've got Harold Locke on Fabulous Friday. It is Scott, Tyler, Simon, howdy. And then we've got, let's see, Billy Beckett is watching. We've got Beatrice Hines.
I thought I saw Richard Grace, Astro Beard, on there too.
Yeah, he's here. He is definitely here. Yep.
Nice.
Richard Grace. Yep. Beatrice is with us. Billy's Astro. And I might have mentioned him already, but there we go. Everybody kind of settles in and gives greetings to each other, which is, these people have all become friends, which is totally cool, you know. Tarek is still trying to decide what the very best, most awesomest telescope is, you know. So one day, you know, he'll probably come back with 3 or 4 of them, I imagine.
Can you hear me now, Tyler?
Yeah.
Yeah, we got you now.
That's really weird.
And Astro for Dummies. I don't, you know.
That's me.
Is that you?
What can we say?
It's a fitting title, don't you think?
I don't know.
It's fitting. It's a fitting title.
Yeah.
I don't know.
Until Nagapan is watching. His kids will be, I think they're going to be on the next Global Star Party, which is kind of cool. So.
Oh, that'll be cool.
Yeah. And Anton's stuck, and there's more, but we'll switch back to Simon here.
Well, we got one question real quick before we jump back in. Josh Kovich. Anyone know if there's a comet near the Christmas tree cluster right now?
There is one in the northern hemisphere that's getting imaged a lot, but it's a long, convoluted name. I can't remember they
all long and convoluted names.
Yeah, no, this is some kind of. I think it's one of the automated observation ones. So it has a catalog name. I'll have a look in a minute. It's been imaged quite a lot recently.
It's not Comet Leonard, is it?
Not sure. I'll have a look. Okay, so we talked about if we undersample our data, we end up with blocky images. If we oversample, we end up with bloated stars. I was about to say neither of them are terrible. They're really cosmetic, you know, in terms of what an astrophotographer would want. You know, the thing about astrophotography is really an art form. It's really what you're comfortable with. But if you're looking for trying to, you know, tune your images and tune your system, then that's what to look for. So we talked about this. Let's have a look at this little table here. This is quite a handy little table, and the way that our sampling changes is with that focal length. You know, we were talking about that pixel size in micrometers divided by the focal length. And this is a real handy table. Remember, we're always trying to get a 1-to-1. So one arc second, well, 1 pixel per arc second is kind of the sweet spot. However, we've already talked that stuff gets blurred through the atmosphere. So it's not a hard and fast rule. And like all rules, they can be broken as long as you know what the effects are. Now, the text here in orange is kind of the band where that you would want to be. And down the side here, we've got micrometers in pixel size, and across the top, we've got focal length. So you can see, you know, if I chose my very fine Explore Scientific 127, which is an absolutely fantastic telescope. If I look at my ASI 2600, which is basically a 3.6 micrometer pixel, you can see here that I'm kind of between 0.8 and 0.92 pixels per arc second, which is kind of just under. It's not bad. I would say that it is that's okay in this area. And if I start to go up in pixel sizes, you know, some of the bigger cameras like the CCD cameras will have much larger pixels. You can see here that the pixel scale starts to grow. And again, you could probably get away with a reasonable level here. Now, if you had one of these telescopes, there are ways, and we'll talk about that in a second, there are ways how you can actually bring your sampling into a better space. Where it also gets tricky, for example, is if you have a camera with a very, very small pixels. So some of the pixel sizes on like the ASI 183, for example, these have only like 2.4 micrometer pixels. Now, you can see if you were to use one of them on a much longer focal length, say we really pushed it out and started to use one of these cameras on, say, the Schmidt-Cassegrain, you can see that the pixel scale really starts to drop and you really start to oversample. And what will happen is that you'll still get an image, but the image will lose its crispness. You'll lose that sharpness. And it would be much better if you then started to look at a camera with much bigger pixels to bring that pixel scale back into that sort of, sweet spot, the golden spot of 1:1. So you can juggle, if you have a camera with small pixels, then, well, what would you aim for? If you wanted the best out of your small pixel camera, then you could aim, that you would have a focal length that's, say, around, 600 to 650 millimeters. That would be something like an Explore Scientific 102. Which is also a really great match. And then if you've got a camera with larger pixels, you can actually stretch it. You could get into the realms of an RC type telescope or even a Schmidt-Cassegrain, depending on the pixel sizes. So, pixel scales is something that you need to have a think about if you want to get the best out of your equipment. It's not a die in the ditch type of, it must be this, 1:1, 1 arc second per pixel. You can actually, go either side of that line. And, hey, if you've got a limited budget and you just have that particular camera and that particular scope, then you do the best that you can. Now, there are ways of dealing with over and under sampling, in post-processing. But like most things, every photographer, even a terrestrial photographer, will say, you get it as right in the camera as possible. Post-processing then becomes a lot easier. So if you can manage, for example, good data, that will help you with post-processing. It'll make life a lot easier. If you are undersampled and have blocky stars, then there are techniques called drizzle, which is a resampling technique that you can get away with, although that can be slightly problematic in that it can return noise back into the image because of the resampling process. Or you can do it the other way. If you're oversampled, you can actually do some deconvolution, which will actually start to shrink the stars as well, but to a limited extent. How do I calculate that? If you want to see it in the real world, then you can use an online tool. So, for example, this is the Blackwater Skies site. In this, you can, on the left-hand side here, we can put in the data that you've got. So, for example, we're going to choose one of my favorite little cameras, which is the ASI 294. So this has about 4.6 micrometer pixels. It's got a horizontal size of 4,144 by 2,088 pixels vertical. And with my favorite scope, the Explore Scientific 127, no reducer or anything on here, and it's got an effective focal length of 952. So if I calculate this out, you can see actually this camera on this setup is actually spot on at 1 pixel per one arc second per pixel, which is great. That's really the best sampling. You wouldn't have to do any kind of post-processing with drizzle or deconvolution unless the atmosphere was causing you some image in terms of blurring. And you can see here, you can see what the scale looks like on various images. For example, you can see what kind of resolution that would give you in terms of an image. If I change this, if I actually put in, say, a much smaller pixeled camera, which is like the 183, if I calculate this out now, and you can see, wow, you can see you've got a much more zoomed in image. But in terms of the scale, you're now at 0.52 arcs per pixel. And that will mean that, yes, you've got a much bigger image, much closer, but you would find the detail would be less sharp because it's actually being captured over a much more wider area in the sensor.
So we do have one question, Simon. It's actually it's pertaining to how I'm thinking of an SCT, and that's what Petka says. According to the table that you just showed, that there's no camera that shows that no cameras is so good for an SCT with a 2000 focal length, or even with a reducer. I can't get to the red scale figures. So what's a good camera for an SCT that has a 2000 to 2800 millimeter focal length? I believe my C11, I know that's 2800 millimeters of focal length, so we're way off scale.
Yeah, let's do that. Sorry, who was that question from?
Petka.
Petka. Okay, Petka. Well, we can use your little example here. If we actually go in and say,
I think an 8 inch.
Yeah, well, we can let's do it on the 11, which will show you a little bit. That's a common size scope with the SCT, so that's there. And let's use the
294, yeah,
294, 2600,
yep.
with no reducer. You can see here, you're down to 0.34, which is very, very oversampled. Great, real blown up view of the horse head here.
Yeah, good detail.
Not the detail would be blurred. If we choose a different camera, and you would have to choose something that would be really one of the big CMOS cameras. I don't know, something like one of the S-Bigs, I think. I'm not sure what the pixel size of those are. There's a 6. But you can see here the sampling at 6 micron pixel size is at 0.5 arc per pixel. So it is a real challenge. I mean, most of the consumer, low-end consumer grade cameras are between 2 and 5 micrometers, and that is a challenge. Now, that's not to say, if you were to choose, I think there is a camera which is the ZWO ASI 2400.
If you choose a full frame, it should.
Yeah, that would close. Be 0.44. Well, you actually just chose. You actually chose touched on an interesting thing there, Tyler. Is that actually the chip size will not affect your pixel scale, and I'll show you. I'll show you this. So if I go here and choose, say, a full frame camera. So the 2600 is the same pixel size as the ASI 6200. They're just a different chip size. So here's the 2600. It's 0.28 on this telescope. If I change this now to the ASI 6200, it's 0.28. So the chip size itself isn't the important one. The two factors are the focal length and the pixel size. They're the two bits. However, what we could do, so let's change this to Practica's little C8, which is a cracking little scope. If we put this on here and put the ASI 294 on there, calculate that out. So there's a 2,000 millimeter focal length, but a 0.47 arc seconds per pixel. The way that you can improve your pixel scales to improve your sampling is to actually use a reducer. And these come in various shapes and sizes. The Celestron one, for example, is one of the screw-on ones. Scott, you do some really good ones. So the ES127, for example, has the really, really nice 0.7 reducer. That's disappearing into the nebula.
Right.
Stand by. There.
So if you put that on there, if we add let's say we put on a 0.7 reducer on here now, you'll see that we're now at 0.67. We're starting to pull that pixel scale back more towards where we should be. It means that in effect, what's happening is that you are actually changing the focal length. The focal length now is 1422 instead of 2000. So as you reduce the focal length, your field of view widens and your pixel scale improves, because actually what you're changing is that calculation, micrometers divided by the focal length, gives you the resolution. So basically you can use that reducer to actually improve your sampling. The other thing that that gives you is the speed increase. Because you're actually capturing more light, because you have a much wider field of view, the overall speed of that telescope will be much, much faster. So in the terms of a refractor, for example, you may have a refractor that is f7. With a 0.7 reducer, you're going to be down to something like 0.56 or somewhere around there. That will mean that you can capture more light for the same exposure length, or if you want to capture the same light, then you can reduce your exposure lengths. That can also help, for example, if you don't want to guide, or you have a system that doesn't guide very well, or on a long exposure. So pixel scales are really interesting, and there's something that you want to think about when you're buying a camera to match a telescope, or you have a telescope and you want to buy a camera and you go, well, what do I work on? The golden rule is 1 pixel arc second is about the sort of the sweet spot, but either side of that is okay, as long as you understand that you may have to do some post-processing, and also that some of that post-processing will deteriorate the image. And the use of a reducer will really, really help if you are particularly badly sampled. Unfortunately, we don't have anything that goes the other way. So you can improve oversampling, but the only way we can get around undersampling is basically to change the focal lengths. So
about binning.
Yeah, binning's an interesting one. You can change the bin size. I don't know whether this calculator will actually allow me to change the binning, but we can do that ourselves here. So let's look at the ES127 again. And these are really good things to be playing with. This Blackwater Skies tool is great. So if we let's go. Actually, what I'll do is actually put that Celestron back in 8-inch HCT with no reducer. So the 294 on its own has a pixel scale, a pixel size 4.6. You can go the other way and go into high resolution mode on this camera, which will go to 2.3. But you'll see if you have a small pixel size on this, I'm just going to change this manually to 2.3. You can see that it really impacts the arc pixels per, arc seconds per pixel.
Wow.
It's down at 0.23 now, so it is very oversampled. But if you had one of these cameras, so if you had a camera with a very small pixel scale, you could bin it, and that effect you would see exactly there by choosing that camera, the 294, for example, choosing a different binning scale. You can actually improve your pixel sampling by choosing a binning. However, binning then does actually reduce the actual vertical horizontal pixel size of the camera. So instead of, for example, 4,144 by 288, you would basically, if you binned in bin 2, for example, your picture would basically be 1/4 of the size of where it was originally, because binning 2 by 2 means you're basically combining 2 pixels into one, which means you're halving the vertical resolution and halving the horizontal resolution. So you end up basically with, dividing that picture by 4, that's the corner. So you would end up with a much smaller horizontal and vertical resolution in terms of pixels. But yes, your pixel scale would be improved. It's a trade-off. And it's a trade-off you might accept if you only have one camera and don't want to buy other cameras and want to make the most of it across different telescopes. Sometimes you just make do with what you've got and do the best with what you've got. And it's amazing what you can turn in, even if it's not perfect. But there are those people will who want the best out of their system, who will buy a camera to match a telescope, or the other way around. They have that camera. Which telescopes can I buy to get the best out of it?
Yeah.
It's always worthwhile having that in the back of your mind, along with all of the other myriad of specifications that come at you out of the screen when you start to look at cameras.
There's always something with this hobby. There always is.
Yeah. So choosing. The other thing is you can choose different reducers as well. You can get some very, very hefty reduction values, 0.6, even like 0.5. The challenge with these is the one you've got there, Tyler, is really nice. It's a 0.7. So that's a good reduction in terms of focal length, which will improve your pixel scale, but also improve the speed of the system. Which means you'll gather a lot more light for the same amount of time, or reduce the exposures if you want it the other way around. Yeah. The challenge with going really, really fast on some of these high reduction reducers is that they can really start to give you some problems with the stars in the corners.
Yeah, that's why you
and then you have to start cropping images. So there's always a trade-off.
There's a trade-off. Peck has got another question. Just for binning, does it make less resolution on the moon or solar for imaging?
Oh, anything, any object you look at. The moon is an interesting one because for lunar imaging, most images would want to use a planetary camera. Mm-hmm. And the planetary camera is a slightly different beast, because what you can do with the planetary camera is you can actually create a very small region of interest. So if you go into something like SharpCap, you can create a very small region of interest around that object, which means that actually you can you can focus on a very, very tiny area rather than the whole thing. So binning doesn't worry too much. The other thing about planetary cameras is that they are usually much larger pixels. Mm-hmm. So that also helps. And also that you are, in general, for planetary imaging, you're using video. So that doesn't tend to worry you too much in terms of that sampling. So there's a kind of specialized case versus deep sky stuff. But you can bin on one of those little planetary cameras, but they're already generally quite a small field of view on them anyway. because they are just such a tiny chip. So yeah, you can, unfortunately, there's no other way. You can't, once you get to a flattener, which is basically the full focal length, there is generally no way of going the opposite way. So unless you change the telescopes. And that's why people end up with, and look, that's why people end up with more than one telescope, because if you want to image, wide field, then that generally is a much different type of telescope than imaging, for example, a galaxy, where you want a much longer focal length. But then, when you've got one camera and you're trying to do wide field or deep sky on a galaxy, you're going to be challenged one way or the other. So you have to make do. Nothing is perfect. Nothing is perfect. And people end up with multiple systems, multiple cameras to do multiple objects. So bit of a challenge. But anyway, I mean, did you have any questions, Tyler? I mean, you and I have been talking about telescope setups and pixel scales and cameras and filters over the last year or so.
Well, I mean, I'm trying to get more involved with understanding how this whole process works, because it is a whole lot, especially for a beginner, because it seems like there's too much information that you can get lost in finding the right answer.
Yeah, the one thing that I found with bringing beginners into astrophotography, it is like trying to drink a cup of water from a fire hydrant. There is, and you have the perfect tool in front of you. You have the internet, and I can guarantee you there'll be people listening and watching going, well, I'm not sure I quite agree with that statement, and that's absolutely fine. That is like any hobby. There are people that will have extreme views. They will have same views of you or opposing views, and for sure, I some of the stuff I look at online, I would go, wow, that's that's an extreme case. But hey, the image came out pretty reasonable. There's long held arguments about monochrome versus color imaging, or narrowband versus color. There's always a differing views. But when you're a beginner, it's really hard to find the right information. And the only advice I always give is to start. Don't buy anything until you've really done some reading, found some knowledgeable people to talk to, and worked out really what you want to do and what you want to image, because it can become an expensive mistake. I've seen so many, secondhand sales on some of the advert pages of, high $20,000, $15,000 mounts and $20,000 a telescope and cameras to match, but the person selling it is completely frustrated because they have that problem. They don't know how to find their way. They're confused.
Tried to throw money at it.
And actually throwing money at it in this is one of those hobbies. I guess it's like golf. You could buy a $10,000 set of clubs, but
if you don't know how to swing your club right, exactly.
Yeah. So it's best to learn from the bottom end. Don't make we're all gonna make some mistakes. We all buy gear and go, oh, why did I buy that? That's actually not worked out for me at all. And then you will find, as you get more experienced, having a good mentor is a really, really important one. And that's
Simon Lewis.
Yeah, I really enjoy. We spent a lot of time together. Sharing information, knowledge, talking online, teaching you, and I really enjoyed that. It's great giving you that experience. I never had that as a beginner. I just had to find my own way and make my own mistakes, and sure, it cost me some money. over the years. But what I have learned is that by going through that process of, pain and suffering, I'm able to, give you the knowledge and others the knowledge that I learned and go, what, you really don't want to do that, because you will end up with this and you don't want that, and that will cost you not only time, but also, lots of gray hair.
Yeah.
There was a question from Beatrice, and she wanted to know if a Barlow can be useful. I put down basically, if you need the extra focal length, to match up the pixel size, then by all means give it a try. But do you have any other insight into using Barlows or?
But Barlows will change the pixel, your pixel scale as well. The interesting thing is that if you use a Barlow, you're going to get a much magnified image from where you were, not necessarily clearer. That's one of the things, if you're doing planetary imaging, if you're imaging, for example, a small object like Jupiter or Saturn, most people will use Barlow just to give you a bigger image on the chip. But again, Barlows, they have their own pluses and minuses as well. But if you get a good Barlow and put some money into one, then they sure can be helpful, particularly on planetary imaging. For deep sky stuff, generally the best way to do it is to get a longer focal telescope. If you need a Barlow.
Now, what would you classify as a sweet spot for deep sky objects? I personally like the 127. I consider that kind of the sweet spot for some planetary and some deep sky objects. I mean, what do you think as far as that?
Oh, look, it is really about, again, matching the target and your chosen type of imaging versus your telescope. So if you want to image galaxies, for example, then you're invariably gonna, unless the galaxy is one of the few really large ones, obviously Andromeda, in the northern hemisphere, is a prime example. You really don't want a long focal length with that, and if you want to image the whole thing. But if you're imaging a much smaller galaxy, then you will want a much longer focal length. A refractor is not going to give you that. Consequently, if you're wanting to image, say, wide field, deep field star, Milky Way, or very large, broad nebulas, then you're going to want to go to a much smaller focal length, because even if you try and do that with a long focal length like the 127, which is about 950 native, and even with a focal reducer, if you put that 0.7 on, it's still like
600,
650, something like that. That's still quite long. If you want to image a portion of the Milky Way, for example, down here we have like the Large Magellanic Cloud and the Small Magellanic Cloud. Well, the Large Magellanic Cloud with the 127, you'll be focused on, say, the Tarantula Nebula, which is one corner of the LMC. If you wanted to image the whole LMC, you would be wanting to use even a camera lens because it's such an expanse over the sky. The SMC, the Small Magellanic Cloud, you can get away with that with, say, an 80 millimeter with a focal reducer. You can start to get that, or it might even be 2 panels. So there is no kind of, for me, there's no kind of sweet spot. It's horses for courses. If I want to do galaxies, I want long focal length. If I want wide field, then you're going to go for a much shorter focal length. And both of those have pros and cons. But where you kind of said, if you were to ask me if I only could buy one telescope, then it would be something in that region of the 127 or the 100 millimeter. You know, the Explore Scientific 102 is fantastic scope because you've got 712 millimeters native. If you put a focal reducer on there, you can be down to, you know, 500 or so. That's good enough to get some of the wider field images in. But also to get some of, you know, young Kieran, one of the guys from the observatory, he's done some really nice images of some galaxies, NGC 300, which is the southern pinwheel down here, one of two called the southern pinwheel, as M83 being the other.
Nice.
That not confusing at all, is it? You know.
No. Not at all.
You can get some real. He can get some real nice images on the 102 native. And then if he wants to do wider, like the Fighting Dragons of Error, which is NG, you know, very famous NGC.
The Fighting Dragons.
6188. Then you can use the reducer and get the whole of the dragons in on either side, and that's where you see these wide field images.
So we got one more question. If you use an 8-inch scope with a large sensor and you crop it, is it better than using, for example, a 4-inch scope with a smaller sensor without crop?
Ooh, okay.
Cropping to match field of view between the two.
Well, cropping is okay if you're rightly sampled in the first case. But cropping won't help you in terms of pixel scales, for example. But you could certainly, if you're well sampled, you can take a portion of a wider image.
Yeah.
You know, so if you got a full frame camera, for example, you know, and you only wanted one small segment of it, you could sure do that. And I have done that. Some of the images I've done, for example, in the Dark Wolf Nebula, for example, is one of them. That's quite expansive. There's a lot of dust clouds on either side of the main sort of main object. But if you want just, you know, one small portion of it, then sure you can crop it in. But to do that, you need a camera that is going to have enough horizontal and vertical size that you can still get a good resolution and good pixel scale and good sampling. So it is an option, but you need to be, spot on the money in terms of scale and size in the first case. As you're just going to end up with, you'll end up with you'll end up with the part of the image you want, but it won't look as good.
All right, so I'm going to close out the show with a joke. I got an email this morning.
I told you, no, not that one. Oh,
I got an email this morning. I thought it was hilarious. How did the black hole lose so much weight?
I don't know, Tyler. How did the black hole lose so much weight?
It's simple. It ate light.
Oh, God.
Oh, come on. But again, I really appreciate, Simon, you taking the time out of your busy schedule.
Yeah. No problem. Really
to teach about pixel scale. Because, I mean, again, pixel scale could be one of those things where you just get lost in all the information because there's so much out there. But hopefully with those diagrams, and if anybody needs access to those diagrams, you guys can send me an email to Tyler at Explore Scientific, and I can send you those to help you just kind of gauge on what kind of telescope to camera sensor you want to get, so you can get those wonderful images and get an A-pod, which I know Simon's got quite a few of. He's actually teaching me. We finally got all my equipment set up, and I finally got done imaging with the 140 FPL 53-140 from Explore Scientific monochrome. So that all got done up last night, and I finished. How many hours have we racked up on that thing? Over 8 hours?
Yeah, 9 hours, something like that.
Yeah, it's my first mono image. I hope it doesn't turn out a disaster. So,
no, and the way to look at it, Tyler, is it's a learning curve. It's a learning experience. And I still pull out images and still, learn stuff. I see stuff on other people's pages, different techniques, etc. This isn't an instant gratification hobby. Astronomy is not, unless you pick up a pair of binoculars, then look up. It's really hard. Once you get into astrophotography, there is so much. My wife asked me the other day. Actually, she said to me, "Why is what you do so complex and so difficult? Surely they could make it a lot easier." And I said, I guess so. And there are some scopes now that are trying to make that easy, but it is a complex thing. You're moving target, dim, long way away, different types of objects in size, composition.
Different spectral emissions.
We're sitting
Everything.
on the ground, we're moving, we've got different mounts, different places on the planet, and then you start to put all this together. And if you just want to take a camera and stick it on the back of a telescope and take a picture, sure, you can do that, and you'll get an image. But if you want to go, into some of these very, very faint objects, it takes a lot of hours, and then you get a bug. I certainly got a bug. Then I want to. A better telescope, better camera. Now I've moved over the last years. I've moved from carrying out my tripod outside into an observatory. Building an observatory and having it fixed, and then automating it. It's I guess it's just like any hobby. You can start off relatively simple, but if you find the bug, then you want to get bigger, better. But getting these extra tools adds additional complexity. It's like any system. The more you add into the system, the more chances are the things that go wrong. And I still get nights where I go, why the heck is that not working? Why does that not do what it was meant to do? It can be quite frustrating. And I think that's what people buy a lot of gear, put it all together, and then go, well, it doesn't work. It doesn't follow, it doesn't track, I don't get an image, I can't focus, and it's like, well, yeah, it's baby steps in this. And that's where you've done well, because you've gone in those baby steps in learning about mounts, learning about the scopes and cameras, and sorry for bringing it up, but
just do it.
There's still little mistakes that people make.
Getting to turn on the mount. Well,
turning on the mount, that wasn't what I was going to mention. Hey, turning on the mount, you spend an hour.
The lens cap off the telescope is nice too.
Yeah,
those kind of things.
Yeah. Why is this not
that
working?
would have been in film days. I have done astrophotographs. The lens cap is still on the scope. So
I spent a whole evening imaging one night here in my early days, and I went outside for about 8 hours, and I'm looking at the images and going, why the heck are these stars got all these huge, great diffraction spikes in them? I'm using a refractor. What the heck is going on? And then I was wrecking my brains for 10 minutes trying to go, what is there something in front of the scope? Oh yeah, I left the button off the scope.
That'll do it.
That'll do it. So I ended up with these really, really fantastically amazing stars with these huge, big, very dramatic diffraction spikes. If anybody's watching, what the heck's a diffraction spike? If you look at these pictures where they've got these beautiful big spikes through the stars, very artistic looking.
Yeah.
Some people like them. Some people add them, and
They do.
But I'm like, why have I got this? Oh, yeah. Dummy here left the button off mask on. Dang. Time to do another night. So yeah, we all make mistakes, and that's the one thing. It's a hobby. Whether it's visual, whether it's astrophotography, planetary, or whatever, it's a hobby for a lifetime. You've got to have some patience. Patience, Tyler.
Huh?
Patience.
What?
So, yeah, you buy some patience.
It's not cheap.
No. Some people are lacking in it.
Well, it was a
So,
great show,
Maybe
everybody.
that's one of the big things that astrophotography does teach you is patience,
Yeah.
so,
Well,
right?
I mean, the good thing is my kids are
You
getting
can
more
apply in
involved.
many areas of your life, so.
So since my kids are getting more involved, or at least my oldest son is, it has to teach me patience because he sometimes can push it.
It's not, you know, and I warn people when they're getting into this, you know, when they, I want to buy a camera, I want to buy a telescope, and I'm like, just be aware, this isn't instant gratification. This is not a social media, you know, put all this together, click the button, and I'm going to get an APOD out of this. It takes years of experience and working, and, you know, long, hard hours of, you know, taking images, throwing data away, reprocessing, you know, learning from that mistake with, you know, turning the mount on or leaving the batten off mask on, and, you know, frustrating. But you know, the way I look at it is I'm out there imaging, and even though I have an observatory, quite often I will just go out and sit out in the chair at the observatory, look at the sky, and listen to the. I've got a big river behind me, and all I hear is the frogs, you know, in the moonlight, and it's just like, wow, this is lovely.
Nice.
It's quiet.
Tarek says it doesn't really teach you patience. You'll just die doing it your whole life.
You certainly send your grave very quick.
Yeah, sounds great, Tarek. I got to get into this astrophotography thing. All right. I did want to share something. You know, Cesar Brolo down in Argentina, he likes to do balcony astrophotography. He uses a pretty modest setup. He set up his.
Yeah, but he could produce a lot of great images from just.
Yeah. Here, let me show you his little setup here. This was, you know, this is his balcony. He's got an Explorer Scientific IXOS 100, and this is one of our first light series. This is not out of our advanced telescope line. This is a 127 Mac, and so he didn't give me other details. He's just firing these images off to me last night as I'm shopping with my wife, and but I enjoyed a couple of them. And so this was the moon shot that he did that night. So it looked like he had some pretty nice seeing from his balcony, you know, and no details of which camera or exposure times or any of that, but we'll have to get him to reveal that maybe at the next Global Star Party. And then you got this pretty nice shot of Jupiter, you know, which
very cool.
You know, so
these are great objects, because one of the great things about these is that they're really, really bright. So you know, even in the city, it's easy to see the moon and Jupiter. So you can you can make the best of it. I've seen deep sky stuff from people in the middle of Tokyo, for example. Doing they've got access to a roof balcony, and they can see the sky, and they use filters and do narrowband imaging and to avoid the city lights. But it's amazing what you can do, and I think that's the most important lesson out of all of it. Have a go, try it. If you've got a home DSLR, if you've got mom and pops, type of a digital camera, have a go. Even the mirrorless cameras, they're really, really great. You can use these and get out, have a go. Try and find a park where you don't quite have so much light, or behind a building where the light is reduced, and just have a go and see what you can do. You don't need to spend tens of thousands of.
And we
I lost him again.
Simon's voice again.
He always has technical difficulties.
Simon doesn't know what happened.
No. And the bad thing is he's in IT. That makes it even funnier.
Oh, that's what happened.
He's getting mad.
He's an IT guy.
But folks, I mean, that about wraps it up. Scott, I don't know if you want to say bye to the wonderful audience that we've had. We've had a great turnout as usual.
We will have a little kind of closing feature video. Oh, you're back now, Simon. I hear you. Simon, is there anything that you wanted to add before we kind of start to close this show?
Thank you again. Thank you for the invite. Pleasure as always. And yeah, I mean, just for anybody watching who wants to try it, get out there and have a go. Don't be worried about, you know, APODs or that it doesn't look like, you know, magazine style image.
Sure.
Get out there and learn. Do it. We have a hunting and fishing company here in New Zealand, and their tagline is "Out there doing it," and it's a really good.
There you go. Yeah,
it's a really great line. Get out there, do it. Have a go. This image behind me was taken on a mom's and pop's DSLR with a single, you know, stock lens. So you don't need you know, tens of thousands of dollars of gear. Get out there and have a go, and that's regardless of whether it's, you know,
you just have to get out there and start doing it. Yep. Right. Yep.
Let's do it.
Simon, what is a good page to have people follow you?
You can find me on Facebook, and if you just look for Simon Lewis and look for the stars and look for the picture of me in my kilt, which is usually the one. Tyler. Okay. Tyler has my contact details as well. So if anybody on the broadcast wants any information, then they can contact Tyler as well. I got time to help people, and you can also find us on the Canterbury Astronomical Society as well, which is cas.org.nz, and you'll find me hanging around. The Pix Insight pages, the ZWO pages, ASI Air pages, numerous other ones.
I'll just share this page here.
Yeah.
Is there a special page you have for astrophotography? I see.
No, just my normal.
And your normal page there with your beautiful wife. Okay, so.
Yep.
All right.
Boss.
There we go. You guys can enjoy that, and I have a little feature video kind of that I've been following the James Webb you know, telescope and its progress and stuff like that, and they're continuing to put out a lot of really cool videos and stuff, so we'll watch that, and you guys have a great weekend. Keep looking up, and we'll see you on Monday.
Beryllium is one of the many elements that people mine, and that's how we obtained it for NASA's James Webb Space Telescope. It exists in many rocks, just in tiny quantities. We collected rocks with the highest amounts of beryllium, crushed them up, put them through many chemical processes, and these rocks only have 0.25% beryllium. To explain beryllium's rare beginnings, we need to talk about the cosmic origins of most elements. When a massive star is forming, it's mostly two elements, hydrogen and some helium. Over time and pressure, temperature builds up in the core, so much that some of the hydrogen atoms fuse, creating helium and officially bringing the star to life. That fusion creates a tremendous amount of energy and is literally what fuels the star and makes the light we see. That star will eventually run out of hydrogen, and the helium atoms start to fuse, creating even larger atoms. That keeps happening, and we get larger and larger elements. These new elements are denser than the former hydrogen and helium, and they cause the star to contract and get even hotter. But that all stops with iron. There isn't enough energy to fuse something more substantial, so once there's too much iron in a star, which means that there's no fuel, it dies, but not without a dramatic exit. The core collapses under the pressure, and all of the atoms knock around into one another, which causes a sort of shockwave, and it explodes into a supernova. This is the energy needed to create heavier elements. This is when more than half of the elements in the periodic table are made. But beryllium is not in that mix. Look at where it is on the table. It has an atomic mass of 4. Much smaller than the heavy new elements. So why isn't beryllium made when the other small elements were? It's just too unstable. If, during the chaos of a supernova, a cosmic ray hits one of these newly formed larger elements, a special reaction happens. This is called cosmic ray spellation. This ray hits a molecule and it bursts into smaller particles. The pieces can continue splitting into smaller parts, some of which turn into beryllium.
It takes a supernova and a cosmic ray to reduce a large element into what could be a variety of combinations and sizes to create beryllium. No wonder it's so rare.